As we scale toward a permanent lunar presence, we are moving past theory into structural stress testing. Today, we analyze grain interlock failure points in compressed lunar regolith simulant, blocks made from synthetic moon dust, under high-velocity kinetic impacts and extreme thermal cycling. One crack in the wrong brick is not a maintenance issue. In vacuum, it is catastrophe. I am on the LSST live desk. NASA's Artemis program is not just about landing boots on regolith again, it is about staying. Permanent habitat modules, pressurized labs, shelters that survive 14-day lunar nights, micrometeoroid strikes, and the slow grind of thermal expansion without the forgiving atmosphere we take for granted on Earth. Here is the math that keeps engineers awake. Every kilogram launched from Earth costs fuel, time, and money. Shipping precast concrete bricks to the moon is not a plan. It is a budget explosion. The alternative is local, lunar regolith, the powdery dust that covers the surface. If you can sinter it, fuse it with heat, microwave energy, or binding chemistry, you turn waste into walls. That is the blueprint for Moon Base 1, not a Hollywood dome on day one. A phased stack of simulant blocks tested on Earth first because we cannot afford to learn masonry by trial and error in a vacuum. In our test program, we work with lunar regolith simulant, minerals blended to match Apollo samples and remote sensing data. We compress it, we sinter it into jagged ceramic-like bricks, then we punish them. First gauntlet, kinetic impact. High-velocity projectiles slam into sintered blocks the way micrometeoroids and landing debris would. We listen for the crack. We measure spall, shards flying off the face. If the brick powders, instead of cracking cleanly, the grain structure failed interlock. That tells us the sinter temperature was wrong, or the binder ratio, or the compaction pressure. Second gauntlet, thermal cycling. The moon swings from blistering sun to shadow cold. We cycle simulant panels through those extremes in chambers, then apply structural shear, twisting and loading the way a habitat wall would flex under pressure changes in settlement. We map microfractures before they become macro failures. Third gauntlet, combined stress. Impact after thermal fatigue. Shear on a block that already took a hit. Real bases do not fail on single perfect tests. They fail where weaknesses stack. What we are looking for is not the strongest brick ever. It is repeatable parameters, density, porosity, fracture toughness, numbers you can feed a 3D printer or robotic bricklayer so Artemis crews lay foundations with confidence. Let me be precise about what this is and is not. These are Earth Lab simulants. Real lunar dust has sharp grains, electrostatic cling, and chemistry we still refine sample by sample. Our impacts smell of scorched ozone in a test hall, not the silent vacuum of the Sea of Tranquility. B-roll shows AI artist concepts and dramatic test stand style footage. The engineering story is real. The visuals must stay honest, the stakes are simple. Artemis timelines push towards sustained surface operations this decade. A habitat wall that delaminates under load does not get a repair truck, it gets an evacuation. So we break bricks on Earth on purpose to find failure before astronauts trust their lives to extraterrestrial masonry. If you are building the future lunar construction playbook, follow LSST Live for the next test series. We will track simulant recipes, impact thresholds, and what good enough looks like when your construction site is the most hostile workshop in human history. Stay curious, stay grounded, and see you on the next orbit.